Good morning again. If you were to find somebody without a background in computers and ask them what they think a lock is and why a database might need one, chances are they'll think that it's a security feature. And as a security feature in the physical world, locks are pretty familiar, ubiquitous really. And anyone who saw an object like the one in the photograph here could pretty much just pick it up and use it to lock up something without thinking about it much. They might perhaps encounter something a little less familiar, but given a minute or so, you look at that thing, you notice that it has keys that look a bit old-fashioned, but you pretty much know you can put them in somewhere, turn it, something inside happens, and your door gets locked. Or you might encounter something even less familiar, where the key doesn't even look like a normal key, and you might fumble around a bit to get it to open or close. But that's all it takes. And even if you have a lock so complicated that you can't understand how it works, even given a diagram of its internals, you don't really care. You put in a key and you can use it to lock stuff up. So again, in the physical world, there are many different kinds of locks. They're good for different things, and some of them are bad for other applications. Some are simple, some are complex. There are old ones and new ones. The only really interesting thing about them is that they're basically all the same. The details might vary, but you use them to lock stuff up. Unfortunately, back in the world of computers, what we call locks are nothing like physical locks. They are not a security mechanism. They're a mechanism we use to synchronize the operation of multiple processes, which is obviously something very relevant to a database engine like Postgres, and relevant to anything that wants multiple processes for performance. They are fundamentally a mechanism to allow you to control how many processes are working on something at the same time. Typically, you use a lock to ensure that no matter how many processes are running, they can't interfere with each other. So typically, you use it to do some operation one at a time. Locks are quite difficult to think about because as programmers for the last several decades, we are used to thinking of computers as executing everything serially, and there being one processor and one random access memory, and your code runs and does stuff, and there's nothing to interfere really. But the more we have to deal with high-performance situations where you need different processes doing different things, and everything running at the same time to the extent that it can, you have to change your outlook to think about how not to let these processes interfere. And as a database engine developer, that's a constant challenge, really. People with some interest in physics might be amused by this diagram. It's one of my favorite thought experiments in physics. It's called Maxwell's Demon. And it's the little green fellow up there who's sorting hot and cold molecules and allowing one of them at a time through the gate. Unfortunately, it's hard to think of physical world analogies for computer locks because in the real world, there aren't many familiar things that operate the way locks do, and it's very easy to stretch the analogy too far. It might help to think of traffic. I live in a village in Uttarakhand, and our roads are pretty tenuous at the best of times. When there are landslides and things, it often happens that you're waiting for several minutes or hours maybe for a landslide to be cleared, and you get this narrow corridor on the edge of the road where one car at a time can pass. If it's a very long landslide, there will be people with a flag at either end who are signaling to each other, these days calling each other on the phone. And traffic gets synchronized in such a way that one car passes in one direction, or a stream of cars, and then they stop and then let cars through from the other side. Same thing with bridges that have limited capacity, or accident sites, construction zones, and so on. I won't speak anymore in terms of these physical analogs to locks, because they aren't helpful. You can draw similarities, but if you want to think about locking in Postgres, you just have to look at what they do. There's a classic example in every textbook of a table that stores your bank balance, and multiple processes trying to decrement and increment the stored balance at the same time. And if you don't get it right, two processes might read the same value and then change them in two different ways. And suddenly you have a balance that doesn't reflect the changes that you actually wanted to make. That's the reason why we need locking in general, and of course in databases in particular at every level. The thing with locks is that if you have one, it decreases throughput by definition. You have many processes running at the same time, and you are slowing them down. You're making some of them, or making all of them perhaps, wait for one process to finish doing something before they can go ahead and do their work. So it is by definition something that reduces performance. And that's a theme we will keep seeing in how locks operate and how we deal with them in Postgres. The reason why we need to slow down performance is, of course, because we can't get correct results otherwise, as in the textbook example. Of course, it's faster to do things wrong. So I'll just speak about locks in general before getting down to specifics about locks in Postgres. One of the things that one has to think about with locks is how long a process holds one. In principle, you could have a process that starts up, acquires a lock, does all its work, exits and releases the lock. If you have locking like that, then only one or two processes at a time can make progress. Of course, it might be one or three or whatever, but you are blocking your processes for a longer period. And the less you do that, the better performance you can get. If you take it to the extreme of holding a lock that excludes everyone and everything for the entire lifetime of your process, then you're running processes one by one, whether they all exist at the same time or not. So that's typically one tries to hold locks for only exactly as long as they are needed, because if you hold them for longer, then you're blocking something that could, you're potentially blocking something that could be making progress as you hold the lock. At the same time, it's not so simple to just take away all your big locks and replace them with extremely short-lived locks and locks that are very specific. We call them fine-grained locks. Because the more locks you have, the more complicated it is to reason about them. The more potential there is for mistakes and interactions that you didn't expect. Contention for finely grained locks at various levels. So it's not just that you split up your locks and all your problems are solved. They're a constant, they need constant attention to correct implementation and to ensure that their lifetime and scope are both as specific as needed and no more. Another aspect of locks in general is how strong they are. And this is somewhere where real-world analogies start to break down. In Postgres in particular, because of the MVCC model that we use for heap data, it's possible to support multiple readers. So you can have several processes selecting from the same table and they don't interfere with each other. They don't need to wait for each other or anything. They just acquire a shared lock and do whatever they want. But if you're writing to the table, then you take an exclusive lock which blocks all activity for the duration of your write, and then release it and people can start using the table again. Processes can start using the table again. Much of the reason we can do things like this in Postgres is because we store historical row versions. So updates and things are not all contending for the same physical set of bytes in your table storage. We create new row versions, and so processes with different visibility of tuples will actually be operating on different parts of the disk. If you attended Pawan's talk yesterday, there was a lot more detail about that. I won't go into it much more. So to summarize, the scope of a lock should be as specific as possible so as to reduce contention, and the lifetime of a lock should be no longer than necessary, again, to reduce contention. And the strength of the lock should be congruent to what you are actually doing with it, what you need to exclude, and no more. So readers shouldn't try to acquire a write lock because it would be pointless and block things that didn't need to be blocked. And generally, as Postgres developers, there's a need to try to do all of these things in the backend so that you get the best performance possible. So now we look at the lock types in Postgres. I'm not sure if the different colors are really visible, but this talk is focused mostly on regular locks. There are also something called advisory locks, which Postgres makes available to applications to use. And then there are several other locking mechanisms which are used internally by Postgres. I have a few slides about those. If time permits, I might go into a bit more detail about that. And poor old memory barriers get struck off because they're not really locks. So a couple of things to start with. The PG backend PID function is something I'll use quite often to identify which process is holding what lock. So in this case, I've just started PSQL, and that value 230693 is the process ID of the backend that I'm connected to. And any locks that are acquired during the execution of queries and things will be attributed to this backend, right? It's not PSQL which is holding the locks, but the server on behalf of the client. And second, I have a table called X. Its contents are not really important, but its OID is 16395, and that's another number that will be showing up in query output once in a while. So this is, so I'll apologize for the very limited query output I'm showing. It's because PGLocks is a really wide table with many columns, and I've tried to fit as much as possible in a readable way onto the slides. Anyway, so this is a query that I'm running in PSQL in a new session with nothing else connected to the database. But you already have two locks. You can see that they're both granted. They're both held by the same backend that I'm connected to, 230.693. And to understand what these are, we actually have to look at more columns from PGLocks. This is everything in the PGLocks table. This is documented in the Postgres documentation. If you look up PGLocks, there's a detailed explanation of each of these fields. I won't go into detail about all of them, but we can split them up broadly like this. So who is holding the lock is reflected in the virtual transaction and PID columns. So PID is, of course, the process ID of the backend. The virtual transaction is not shown here because it's big. The lock type, mode, and granted, which are seen here. The lock type is relation, mode is access share lock, and granted is true. I'll go into detail about those. That reflects what kind of lock the process is holding. And finally, database, relation, page, tuple, virtual XID, transaction ID, and so on, are the columns of PGLocks which tell you what the lock is being held on. So depending on which locks the backend has acquired, these columns will have different combinations of values. So for example, if the lock is on a relation or a table in a database, then you can expect OID values for the database and relation to be filled in. But if it's not a relation lock, if it's a lock on something entirely different, we'll look at examples, then those values might be null. And if you go back to the output here, we know that our backend is now holding two different locks. One is a relation lock. We don't really know what that means yet. And one is a virtual XID lock, which I'm not sure, even after so many years of using Postgres, I'm not convinced I understand it. But we'll look at it anyway. So these locks, which are in PGLocks, at least the ones that we've seen so far, are the same locks that Postgres, the same kind of locks that Postgres acquires during its normal operation. They are not locks that you have to ask Postgres for. You just run queries, and Postgres knows which locks it needs and goes ahead and asks for them. There is a lock table command by which you can explicitly ask for these same kind of locks. If you do so, then of course the locks you're holding may conflict with other Postgres processes. So you might, if somebody is already holding a lock on a table and you try to lock the table, your backend will just wait for the lock to be released so that it can acquire it. So you can add no wait to not block and so on. And the other interface to these locks that is available to users is select for update, which is a statement many of us may have encountered. And that takes a different, it acquires row level locks rather than table level locks, which is what lock table does, as the name suggests. This is just a bit of background on, yeah. The point of this slide was just that we have access to the same locks that Postgres uses internally. So these commands are useful to play around with in PSQL sessions and look at pglocks output to see what happens. Okay, so again, going back to the output here, the mode column, access share lock and exclusive lock, corresponds to the lock modes for the lock. There are several modes available. The ones listed here are just the weakest and the strongest, respectively. Access share is a lock mode that doesn't, that isn't blocked by any, or that doesn't block anything except access exclusive. So it's the lock that select queries will acquire on a table as it runs, and any number of processes can lock the table with this mode and not trouble selects, not block selects. Only if another session wants to acquire an access exclusive lock will processes that hold an access share lock be blocked. So for example, if you are trying to drop the table, then you have to wait until all the sessions that are selecting from it have released their lock. Okay, one more thing I forgot to mention here. There is no unlock table command. Any lock that you acquire is released at the end of your transaction or at the end of the session. Yeah, that's all I have to say about that. So at the end, please. Yeah. I'll come back to it, no worries. So these are the other lock modes that are available in Postgres. So in between access share and access exclusive. They are locks that are held by different classes of DDL commands and so on. But fundamentally, there's nothing different about these kinds of locks. It's just that there are rules about what conflicts with which other lock mode. So we'll look at a few examples. But for example, share locks in the middle there with create index are not blocked by select commands, for example. Yeah. So these are table level locks that we've looked at so far. And there are also row level locks, which I mentioned you can acquire through select commands, or which Postgres acquires by itself, for example, to do foreign key checks and so on. These are the 4 modes, and again, in this case, it's in decreasing strength. Sorry about that. So going back to our PSQL session, here's one session where I start a transaction, and the backend is 247196. And here's another session with a different number. And if I look at what locks there are already, just with an open transaction, no other queries. So you see one access share lock, which is the lock that select acquires, on relation 11645, which is granted, and it's held by 170, which is my second session as it happens. Does anyone want to guess which relation this might be? Okay, yeah, it is pglocks because of this query that's actually running and whose output we're looking at. So this is obviously a lock acquired by this backend because of the query we ran. The other locks are these two. I split up the output to fit in the slide. So each backend holds one exclusive lock on a virtual XID, which is granted, and I seem to have forgotten to include the virtual XID. But this is just something that you have to be familiar with, because any transaction that runs will hold an exclusive lock on its own virtual XID. So many of the entries in PGLocks, if you have many transactions running, will follow this pattern. They'll have a lock type of virtual XID. The mode will be exclusive lock, and it'll be granted to the process that's running that transaction. Okay? Yeah. The reason for having these locks will become clear in the next example. So now in one session, I run an update command. My X table has a column which has some integer values, so I just double them. And in the other, and note that these are both running in explicit transactions because I ran begin in PSQL. Right, so my update runs and completes. And in the other session, I have run select star from X for update. So I'm trying to acquire for update row lock in the second session. Now, the problem here is that the first session has already acquired locks on that table to update it. And we can see here, again, severely compressed output. It's ordered by PID, so the first 4 locks are held by one session, the one that did the update. The last 4 locks are held by the session where I ran select for update. The yellow thing in the middle is a lock that isn't granted. So what happens is that the second session, or Postgres realizes that the second session needs to wait for the first transaction to complete before it can acquire the locks it needs. So it's trying to acquire a share lock on the transaction ID that the other transaction already has a lock on, which is this sort of lock that we looked at before. So here, if I commit the update transaction, the select from update, which was hanging until now, suddenly returns 2 rows. And if you look at PGLocks again, the transaction that ran the update and which has now committed does not have, it had 4 locks before. Here are the 4 locks. It doesn't really matter what they are. But it has released them, and now 247196 has a row share lock on the relation. 16395 is the OID of the table X. So PGLocks is a really useful view in the Postgres catalog. It has all of the information required to figure out what your backends are waiting for if they're waiting for locks. It's tempting to write a giant join against PGLocks to find out which session is blocked by which other session, and if you spend a very little time searching for such a thing, you will find several versions. But the problem with these queries is that the actual conflicts between the various available lock modes are not, they're not straightforward. It isn't that the locks conflict with each other in increasing order or something like that. Some operations block others and some operations don't. And there is a constant effort to block less and block only when necessary. So this is actually something where we make improvements regularly, as anyone who attended Simon's talk about schema upgrades yesterday will have heard. So in Postgres 9.5 and above, there is a function called PG blocking PIDs, which knows all this stuff, and which is much better than trying to roll your own query. So if you have a situation where one backend is waiting for a lock, which means that granted will be F, then you can just select from PG blocking PIDs for that backend, and it'll give you a list of backends that actually hold the locks that this backend is waiting for. So in this case, 245562 is being blocked by a lock that is held by 245547. And that lock looks like this. In this case, it's a share lock on the transaction that it's waiting for, and this transaction is running, so while it is still running, that is before, until you abort or commit it, this other session will be blocked by it. Yeah, okay. So here's an example of, okay, pretend that I stepped slightly backwards in time. I didn't commit my update transaction and those locks are still held. If I try to drop the table while the locks are held, it waits to acquire a lock, fails because I'm not committing my transaction. And because I have set the lock timeout to 3 seconds, after 3 seconds, it cancels the drop table statement because it isn't able to acquire the locks that it needs within the stated timeout. And this is the lock that it's trying to acquire. It's an access exclusive lock, which you may recall is the strongest lock type. It is blocked by any lock held anywhere else in the system on that relation. The relation, of course, is our table X. And similarly, other DDL statements take different modes of lock on the objects that you ask them to operate on. So for example, if we create an index on our X table, it actually works while I'm still holding the locks on the table because it needs only a share lock to scan the table, as we saw in the table of lock modes. Which is not exhaustive, by the way, that those DDL statements are just examples of what acquires that lock mode and not a complete list. So here again, the create index completes, but drop index needs an access exclusive lock and is canceled because I'm holding that lock and it couldn't acquire it in 3 seconds or whatever. The PG stat activity catalog table will also give you some insight into backends that are waiting for each other. So in recent versions of Postgres, the wait event type and wait event columns will tell you when a backend is waiting for a lock. So this will correspond to a lock request in PG locks that is not granted. So looking at locks where not granted in PG locks is often interesting when you have performance problems, for example, because a lot of times performance problems that show up when you have many concurrent clients might be due to them trying to acquire the same locks and slowing down to a crawl because only a few processes can acquire it and make progress at one time. So the combination of PG locks and PG stat activity with the PG blocking PIDs function can tell you a lot about what kind of locks are held on your system while it's running and what kind of locks are being waited for the most and which take the longest time to grant. So I think this slide should have been one thing earlier. But create index is just one example. Any other DDL command you run on the table will need some varying lock on the table or the index or whatever you're operating on. All of that will be reflected in PG locks as the query runs. Okay, so how am I doing for time? Okay, I have some time. Advisory locks are another class of lock in Postgres. The difference between them and regular locks is twofold. One, Postgres does not use them. You can, as an application developer, acquire advisory locks and do whatever you want with them. They will not interfere with any locks that Postgres itself acquires or holds during normal operation. But they do show up in PG locks, which is useful to figure out if there are locking problems in your application that you need to analyze. And the other difference is that the interface provided, the interface by which you interact with advisory locks is a bunch of functions that you call, which we'll look at. What you lock in advisory locking is just a 64-bit integer in one form or another. They're not database objects because we don't want these locks to conflict with anything Postgres is doing. So it's just numbers. You can lock whatever number you want, and what that means is up to your application. Advisory locks may be transaction scoped. So you acquire an advisory lock in a transaction, and it will be released when your transaction exits, which is just like Postgres locks. Or they may be session locks, where you acquire the lock, but it will survive the end of your transaction and will be released only when your session ends, when you close the connection to the server. And again, like Postgres locks, they can be acquired in either exclusive mode, where only one process can use them, or shared mode, where multiple processes can hold the lock simultaneously, but not if anyone has the exclusive lock already. So this is what the interface for session-level locks looks like. The PG advisory lock function will acquire a lock on the key that you provided. This particular function acquires an exclusive lock with session lifetime. In this case, there is also a PG advisory unlock function, which you can call explicitly to release the lock before you close your session, or whether you close it or not. But with transaction locks, there's no explicit unlocking. They work the same way as Postgres regular locks do. You acquire the lock with this function. It's still an exclusive lock, and when your transaction commits or aborts, it's released. So this mechanism actually is very convenient if you need to do locking to coordinate between multiple processes in your application, but you want to do so in a way that does not affect Postgres. And so all of this will be invisible to any DDL operations and stuff, so it won't cause any conflicts. Rather than exclusive locks, as I said, you can acquire shared locks with either session or transaction lifetime. They're just like the other locks, except you use a different function to acquire them. And they conflict with exclusive locks. So just like you can't drop a table while sessions are selecting from it, you can't hold an exclusive lock while there are active share locks on the same key. So 42 in this case. Also, as I mentioned, there's a no-wait keyword that you can provide to lock table in order to not wait for the lock if it isn't immediately available. Advisory locks have an equivalent called PG try advisory lock and so on, which work just the same way. It's just that they don't wait if the lock is unavailable. They just return true if it could acquire the lock and false otherwise. So your application can try to acquire a lock, and if it fails, rather than sleeping, it can go on to do something else. It's just convenience. As I said, advisory locks will also show up in PG locks. The lock type will be advisory, The mode will be whatever you acquired. And the key that you're locking will be stored in these columns of PGLocks, which we hadn't seen any values for before. But it just underscores that what you're locking is not a table or a row or something like that. It's a user-defined value. What it means is completely up to you. So with advisory locking, there's an, well, actually, with any sort of locking, it's easy to have two sessions that acquire locks that conflict with each other. In this case, suppose sessions A and B are running together. One acquires a lock on 1, one acquires a lock on 3, and both of them succeed. And then A tries to acquire a lock on 3, and B tries to acquire a lock on 1. Neither succeeds because the other session is already holding the lock. So they will either just go to sleep or be unable to make any progress because of the fact that B will not release the lock on 3, so A cannot progress, and vice versa. So basically, both of them are blocked by each other. In this particular case, because we're using advisory locks, Postgres doesn't care. It'll just do whatever and leave your two sessions blocked forever if that's what they're inclined to do. But the problem is not with advisory locks alone. The problem applies to any kind of locks that you acquire. And Postgres does actually have something called a deadlock detector, which specifically tries to address this problem where one session holds a lock that is required by another session, and that session is waiting for a lock that is held by someone else. It doesn't have to be just two sessions. It can be a complex cycle. You might have deadlocks between a group of 6 sessions. It's the kind of problem that tends to show up only under high concurrency. And when it happens, it may be quite hard to track down because of the number of processes involved and the copious PGLocks output which you have to examine to find out what's going on. So the general solution to this problem is to acquire locks in some kind of predictable order. So if A and B in my earlier example had both tried to acquire a lock on 1 first and then 3, this problem wouldn't have existed because A would have acquired, let's say A would have acquired the lock on 1 first, B would just be waiting, A would successfully acquire a lock on 3, go on to do something and presumably exit releasing the locks, and then B could start doing whatever it wanted to, and the problem would go away. So inside Postgres, this is a pattern that is followed consistently in order to avoid just this problem. But this problem may not, so there are two possible sources of the problem. There might be a bug in Postgres that causes it to lock something in an unpredictable order and create a deadlock. But much more likely is that your application is doing a series of operations that causes a deadlock. So Postgres has nothing to do with it, but the way the application uses the data, it's creating a situation where you're just waiting forever. So Postgres has a thing called the deadlock detector, which is quite expensive to run, but it detects such situations, and it will abort waiting transactions in order to let other transactions progress. This is obviously not an ideal situation, but when the deadlock detector is invoked and finds a deadlock, the system will otherwise not make any progress at all. Those sessions are blocked forever and can't do anything but quit. So it's a last-ditch resort. There are 3 configuration parameters that are especially relevant to the subjects we've discussed so far. Lock timeout is something we already saw, which controls the amount of time we wait to acquire a lock. Deadlock timeout is a similar timeout that allows us to set how often the deadlock detector will run. And log waits is something that will create log entries when the deadlock timeout expires. Yep. And there are logs pending. I have a few more slides about some slightly arcane topics. Is anyone interested in carrying on, or should I stop here? Yeah, stop. Fine. So if anyone is interested, please find me after the presentation, and I will be happy to go through this for you. In summary, look at PGLocks, learn to understand what it says, and it will tell you a lot about what's going on in your database. Any questions?
Yeah, hello.
Yep.
So basically, I have just basic question. So when you specify explicitly for the particular log, you let the Postgres decide which particular log he wants to acquire for a particular query. So what's the difference between these two?
So most of the time, you don't need to do explicit locking. The only reason I brought up explicit locking is because it gives you a way to find these, to acquire these locks and look at what's in PGLocks. So most of the time, you just run your select or update or whatever, or your DDL statements, and leave it to Postgres to decide what locks to acquire.
So is the guidance for a log to a Postgres makes the query run faster anyway?
No. If there's a lock, it'll run slower. But that's what you want because it's for correctness. There was a question here earlier.
You want to ask a question?
It was a rather naive question. On one of your slides, you had a list of PIDs.
Yep.
And then you're talking about log type. So I was just wondering if practically I ran a debug version of PostgreSQL and then attach the debugger to that PID. Can I traverse through data structures from which I can actually extract that information which you were showing in those columns?
Yes, in principle, but the interesting data structures will be in shared memory. And so you don't really want to trample with them when there are other processes running. But yes, of course, all of that information is in memory, and you can look at it in a debugger.
All right, okay.
Yeah.
Thank you so much.
Sure. Any other questions? Yep. Thank you all very much for attending my talk. I hope it was useful.